So there is, as I said, so we are still going to stick to diffusive kind of processes, but not do the analysis the way we did in the previous session. Okay. We'll now basically we'll say that system has some states. So for example, xn, where such that n goes from 0, 1, 2 and so on. So you would say that these are the states of the system. So just to give you an example, let's say if you're talking of weather, you could say either it's sunny or maybe it's raining or it's snowing, whatever. So that is 3 states of the system. So you can create any number of states, and maybe your weather is going from being sunny to state which is raining, or rainy to snowing, and whatever. Okay. So you can look at this entire process of random changes that's happening in terms of going from one state to another state. So which means that your basic objects of interest now are these states, which could be labeled as xn. And you need to describe the probabilities for such a process from happening. So for example, we could ask for, let's say, the probability that x0 is, so x0 is your random variable. It takes, it's the state which takes value I0. Okay. And maybe x1 takes I1 and so on, and maybe xn takes In. So let's say that I write this quantity which I call the probability for the state to be in In, given that it started at I0 and x1 was I1 and so on until xn minus 1 was I minus 1, In minus 1. So which is basically a statement that, if you talk in terms of random walk problem that we had, it's basically saying that the random walker started at position 0, then went to maybe position 1, went to position minus 1, maybe then minus 2 and so on, and currently is at some position xn. You written the probability that there is this sequence. The Markov property basically says that it doesn't depend on all that history. You don't need to worry about such a long pass. Just worry about the last step alone. Okay. So it's essentially saying that I'll write this in terms of xn equal to In, given that xn minus 1 is equal to In minus 1. Because as I said, random walk is an example of a Markov process like this, where your next step depends only upon where you are currently, not where you were like several time steps back. Okay. All that is immaterial where you came from. So this equation here encapsulates this Markov property. And another assumption is that transition from one state to another state is time dependent. So whenever you are going from, let's say, again, to give you back the random walk example, let's say you go from position minus 2 to minus 3. Okay. That probability is time independent, the transition probability. And in fact, that is the condition under which we worked out all the earlier rules. The small p and small q were all time independent, didn't depend on time explicitly. So what you have is a set of these states, and the claim is that there is a probability for transition to go from one state to another state, and these transition probabilities are time independent. Then this kind of a structure is what you would call a Markov chain. The transition matrix for the Markov chain will be a n by n matrix. So, which means that you have n states. So, let us say that assuming I have n states, the transition probability will be a n by n matrix whose ijth element ijth element, which will be some small pij, gives the transition probability to go from I to j. So, these elements Pij, since they are probabilities, they will of course lie between 0 and 1, and this I and j, which are indices, they will of course go from 1 to n, provided you have n of those states. And one further constraint is that this Pij, since it's a transition probability, summed over j will be 1. Okay. So, I'll show all this with the example. So, it might all look a bit hazy now. So, any matrix which follows these rules, the rules that we have written down here, this one, and this constraint, this normalization constraint will be called a Markov chain. Okay, so let's consider a very simple two-state Markov chain. I just have exactly two states. Okay, it's a so you can, for example, imagine that it's a model for maybe a telephone exchange or a phone call. So there are two states. Xn could be either 0 or Xn could be 1. So if it is 0, you say that the phone is free, or if Xn is 1, you say that the phone is busy. Okay. So the fact that phone is free is one state, and the fact that phone is busy is another state. Yeah.
Matrix, what do you put P I? I to I. Do you have any zero?
I to I, it depends. It could be 0 or it could even be 1.
There can be systems which can.
Yeah, which can have 1. Yeah, there is nothing predefined for that. And in each time interval, you could have a situation where we'll define this small p, which will be the probability that a call comes in. So this is a probability that a call comes in a particular interval of time, and obviously 1 minus p is the probability that no call is received in a particular interval. Now you can actually, so you have two states which we are labeling, let's say 0 and 1. Now you can actually write the matrix P, the transition probability matrix. So for once, let me just write the labels as well. So for example, the 0, 0 element here, what is the probability that at previous time interval the phone was free and in the next time interval also it is free? So that would be 1 minus p. So that is basically the transition from being free to being free itself. And the next element, 0, 1 element, is what is the probability that it was free and a call was received at the next time interval. That will be p. Okay. So similarly, you can interpret the other two elements, that it was busy and then became free. That's just q and 1 minus q. So now you have constructed a transition probability matrix for this simple two-state system. Question is either the phone is free or busy. Those are the two states in a given interval of time, and you have defined the probabilities for such a process and you have encapsulated all the information in this transition probability matrix. And by assumption and also by the statement of the problem, in this case, these P's and Q's, which are the basic probabilities, they don't depend on time. Okay. And you will already notice a few things. First is, you notice that all the elements are positive. Okay. The elements of this matrix are positive, and if you sum along the rows, it is 1. So every row sums to 1. So 1 minus p plus p is 1, 1 minus q plus q is also 1. So this is not just the artifact of this problem, it's actually true for all the transition probability matrices that we'll meet. So I'll go through a series of examples like this. In all the cases, these properties hold good. And I mean, you can imagine why it sums to 1 along a row, simply because the phone has to be either free or engaged at any particular time. Okay. There are only two possibilities. Okay, so this is your transition probability matrix for such a case. Now let's add a little bit more to this and go to the second example. So we'll look at what we can do with these kinds of matrices after going through 2 or 3 examples of constructing these kinds of matrices. But now suppose I say that I allow a call to wait, in the sense that either the phone is free or a call has been received. Earlier we didn't have a situation where when one call is already on, one more call can come. Now let's say you allow for that, which means that the second caller will be put on a queue because the phone is busy. So which means that now you have a three states that are possible. Your state space will now be 0, 1 and 2. Okay. So 0 and 1 correspond to the standard previous case. Phone is free, phone is busy. 2 is when there is a call waiting in the queue. Yeah, so probability of going from 0 to 1 is small p, and the probability that of 0 comma 0 is 1 minus p. That's exactly what we had written in the previous case. What about this probability? Probability of going from 0 to 2. That will be 0 because because when the phone is free, there is no question of putting someone in the waiting line. So this is 0. Okay. Now similarly, you can actually write down the other probabilities. For example, what is the probability of 2 to 0? From the wait straight away going to free is not possible because the person waiting needs to get in. So this will again be 0, and p 2 comma 1 will be simply q, and p of 2 comma 2 will be 1 minus q. So this p of 2 comma 1 is simply the probability that call is completed and P of 2 comma 2 is that the probability that the ongoing call is not yet complete. Now let's do this probability of 1 comma 0 uh, is q into 1 minus p. This is simply the probability that call completes and no new caller comes in. So just think for a moment why it should be like that. It's straightforward. Okay. And p of 1 comma 2 is p into 1 minus q. Okay. Again, this is a probability that call is incomplete and a new call comes in. And p of 1 comma 1, you simply do a 1 minus these two elements. Okay. So if you do that, you will get 1 minus q into 1 minus p minus p into 1 minus q. So now assemble this entire information in your probability transition matrix. So this is your probability transition matrix. Once again, you notice that all the numbers are 0 or greater than 0, and every row sums to 1. You can actually represent this in terms of a graph. Since you had 3 states, you will have 3, let's say 3 nodes like this. So let's call it 0, 1 and 2. Now you can draw directions. For instance, okay, again maybe one more. So this is 0, 1, 2, 0, 1, 2. So 0 to 0 is 1 minus p. So I could draw something like this and say that this is 1 minus p. And 0 to 1 is simply p. So 0 to 1 is p. And 0 to 2 is 0. I don't need to draw anything. 1 to 0, which is this, that is q into 1 minus p, and 1 to 1, which is a self loop. So that's 1 minus q into 1 minus p into 1 minus q, and 1 to 2 is p into 1 minus q. 2 to 0 is 0, so don't need to do anything. 2 to 1, 2 to 1 is q. 2 to 2, you have a self loop, 1 minus q. So this graph has all the information that you want to calculate anything that you want. So this is a directed graph because you have directions. Okay, now if you get the hang of what we are doing, now you can go back to random walk and write random walk in terms of these transition probability matrix. Okay. So let's do a slightly different kind of random walk problem. So now this is example 3 is a random walk with reflecting boundary. And I am going to do this on the following states. N. So it's going to be a random walk with reflecting boundary. Basically means that it's still a one-dimensional walk, but when the walker goes at the end, basically the walker turns back. That's all.
If it takes the right move, it comes back to 0 or it comes back to n minus 1?
N minus 1, no question of going beyond the lattice. There's nothing there. So yeah, okay, maybe you can even draw the lattice. So this is 0, 1, 2, and this is n. There is only one choice. With probability 1, you have to jump back. That's all. So if you are at n with probability 1, you can jump back. Okay. So that is what we will encode in the transition probability matrix. So let's say that p is the probability to take right step. And of course 1 minus p is the probability to take step 2 left. And at the boundary you have to treat it differently. With probability 1 you will reflect back. So now you can write the general results. So the probability to go from I is index for any of these 0 to n, going from I to I plus 1, which is taking a step to the right, that is simply p, and probability of going from I to I minus 1, which is taking a step to the left, that is 1 minus p. So this rule will apply provided your I lies between 0 and n. So it does not specifically apply to 0 and n itself, anything in between it applies. And for the last nodes, probability to go from 0 to 1 is 1, and similarly probability to go from n to n minus 1 is also 1. And if you want, you can add that p I comma j is equal to 0 for all other I comma j. So here you can choose a value for p. You can, for instance, unbiased walk, you will choose small p to be half. So 1 minus p is also half. Then you can write this in terms of a matrix. So in this case, you will get a n plus 1 by n plus 1 matrix. Fill in the elements. Okay, I will not do that, but straightforward from here. So the point is that you can treat your random walk problem in terms of this transition probability matrix. Similarly, one more example with random walk. So random walk with absorbing boundaries. So absorbing boundaries would mean that if the walker goes to either 0 or to n, basically the walker dies there. So that state absorbs that walker. Okay. So in this case, so once again you have states going from 0, 1, 2 up to n, and you can write the probabilities as going from, probability of going from I to I plus 1 is p, and probability of going from I to I minus 1 is 1 minus p, and this of course is valid only when I lies between 1 and n. Okay. And then probability of going from 0 to 0 is 1. So if a walker steps on to 0, it stays there forever. And similarly, if the walker steps on to nth state, it stays there forever. Okay, no question of coming back or anything like that. So in this case, you will see that in both these cases, both these random walk variants that we saw will generate for you a tridiagonal matrix. Okay. So for example, if I take n to be 4, so which means that the possible states are 0, 1, 2, 3 and 4. Okay. So in that case, the transition probability matrix would look like, this is for the absorbing case, 1, 0, 0. So there will be 1 at the top and at the last right corner, and in between it would be like, so this, let me use q, so it will be q 0, p 0, 0, 0, q, p 0.
I can't be I one is the first.
Huh?
I can't be one is the first.
I cannot be 1 in the first definition. Why?
It should be 0 less than I. And 1 is 0 0 less than I. 1 less than or equal to I.
Yeah.
The first equation, p of I comma I plus 1 equal to 3. At the end.
Oh, I see. Okay, okay. At the end, you mean?
Yeah. 0 is strictly less than I. Only because 0 doesn't apply.
Yeah, it doesn't apply for 0 alone. Yeah.
So 1 is inclusive.
1 is inclusive then. Yeah, correct. So I should just put, or actually I should just put it as 0 here. Okay, so you get the hang of it. Now let's do it. The nice thing about it is that now it's easy to extend this to a general graph compared to the kind of analysis we did for random walk, which is very specific to the kind of one-dimensional lattice that we took. We go through an extremely hard amount of mathematics to get the results. But now let's say, for example, I can draw a different general graph. So I'll do a simple random walk on a graph. Okay, so let me draw some arbitrary graph like this, maybe with 5 nodes. Okay. So how do you implement random walk on a general graph like this? Earlier it was very simple, you just had 2 directions. You either took half or whatever ratio, but the sum has to be 1. But now the general way of handling random walk on a graph like this is that your probability of transition from any ith state to jth state, here it would also label the nodes, ith node to jth node, will simply be given by 1 divided by the degree of the ith node. Okay. So you know the degree, what the degree is. For example, the degree of node 1 is 3. Degree of node labeled 1 is 3 because it has 3 connections and so on. So which means that the probability for any walker who is at node 1, such a walker can only go to 3 possible places. The walker can either go to 4 or to 2 or to 3. So the probabilities will be 1 by 3, 1 by 3, 1 by 3. So that's basically 1 divided by the degree, which is 1 by 3. So similarly, you can apply the same principle for every node. So the general formula is that the probability of transition is 1 divided by the degree of the node in question. So even when one of the problems in the problem set that I have given is to simulate a random walk on a general graph like this. So you need to know the degree of each node to be able to do that random graph. PII should be 0. Yeah, that's right. So yeah, we can even mention it explicitly. So in the standard random walk scenario, there is no possibility for the walker to stay in the same place. The walker has to keep moving all the time. So all these PII will be 0. So you can actually also state that this is true provided this Aij is equal to 1, where this Aij is simply the element of what is called the adjacency matrix. So adjacency matrix, let's say, is A, and so element Aij will be 1 if I and j are connected, if there is a link between I and j, and this Aij will be equal to 0 if otherwise. So it's a easier way of capturing the information about the graphs. So we'll keep using this adjacency matrix many times as we go along. Now, why is this useful? So till now we have been writing these probability transition matrix in some of these examples, we really did not do anything more than that. Now we should try and start using the information that's available in this probability transition matrix. So one thing you could ask is, for example, you can define a n-step probability, which is denoted by so this, which is denoted as Pij, is the probability that the initial state started from I, and at nth time it is in state j. So that is what this notation means. Actually later on I am using the notation slightly differently. I would have actually written it as Pn of I comma, so Pn of I comma j, I would state it as the initial state is in j. After doing n steps, what is the probability that the walker is in state I? Okay. So maybe to fix your ideas, let's say that if I have some 10 states, 1, 2, 3 up to 10. So I am asking the question, my Markov chain, it could be a random walker or anything for that matter. My Markov chain starts here. At time t equal to 0, it was in state 1, and I am asking the question, let's say after n steps, maybe n, let me take it as 5. After 5 steps, what is the probability that the walker or the Markov chain is in state, let's say 6, for example. So that's the probability that is mentioned in somewhat general terms there. So typically in most cases, this it's only the time intervals that matter. The starting point being 0 time is basically a label that you had given. I can take this instant of time as 0 of my life, for example. No one to complain. So that arbitrary choice of the initial time is immaterial. So such walks are called, such processes are called homogeneous, okay, where only the intervals matter, not the labeling of the starting time. So which means that I could have equally written this as like this, n plus k equal to j given xk equal to I. Simply I have relabeled 0 as k, that is all. Now you can ask the question, what is the probability that xn is in j? Then all you need to do is to sum over all possible starting points. So you would say that I'll sum I over all possible states in the state space, which would over this probability. So I want xn to be j, but I'll sum over all xi's, okay, or so this is your final probability that it is in j. Now these probabilities that you are getting, for instance, Pn I comma j will simply be the ijth entry in the transition probability matrix. So this can be proved. I'll skip the proof doesn't do. Huh?
This problem is the order of power n. This is n step. This is n one.
This is a n step. Yeah, so it will be actually to the power n. Yeah, that's right. Yeah. So it will be the in the transition probability matrix to the power n. Yeah. So now you can actually specify an initial condition like this. Let's say that this is my initial condition at t equal to 0, which I will write as 0 of 1, come on. So if I have a n states, I am specifying the initial probabilities in n of them. Again, going back to some example like this, you are saying that what is the probability at initial time of being in 1 or 2 or 3 and so on. So that is that vector. So given the initial probability like this, you can actually calculate the distribution of let's say walkers at time n. So that will be phi n bar is 0 p power n. So that is where this transition probability matrix is useful, because you can write an equation like this. So you raise, because you have, let's say you have some initial condition. Which one? Not q, phi. Phi naught is the here is the initial distribution over n states.
Probability that the guy can be in the.
Yeah. I'll show you with the example, maybe you will appreciate it better. So you are given the initial, let's say that in the initial time you can be in any of these 10 states, and you specify that as part of this phi 0 vector. Yeah, it will be a vector because you'll have to specify probabilities for being in each one of them. So you have n states, you'll have to, and that all the elements will sum to 1. That is at initial time, that's your starting point. Now you want to ask, how does this evolve after n steps? And that is given by this equation. Okay. So you simply raise p to the power n and multiply it to the initial probability vector. You will get how that probability vector has evolved for time n. Now let's do an example. I think that will give you a better idea of how we are taking it. So let's go back to that first example, the two-state problem that we had. No. So this is a row vector. So that's why I wrote it as a row vector. Yeah. So you can also write it in terms of column vector. The equation will look different. That's all. Yeah. So in the standard format, we write it in row vector simply because rows sum to 1. So you can transpose your probability matrix such that columns sum to 1. In that case, you can write in a more familiar way where P acts on a. You can do that as well. But most textbooks follow this convention. Yeah. So let's go back to that two-state problem, that phone problem that we had. So let me to recall that problem. So it's that example 1 that we had earlier, and remember that P in that case was 1 minus P, P, Q and 1 minus Q. Okay. So let me now take my initial, let me assume that phone is free at initial time. At initial time, which I will take it as time t equal to 0. In that case, what would be my phi 0? That will be 1 and 0. Yeah, okay, maybe I should write it as a row rather than. Okay. And now let's give some numbers so that we can calculate. So let me, since I've already calculated it for p equal to 1 by 4 and q equal to 1 by 6. Okay. So this is part of the problem statement, these numbers. Okay. So everything here is part of the problem statement. So you are given the p values of p and q, you are given the transition probability matrix which you can construct, and you are given the initial condition. Now the question is what happens at n equal to 6, let's say. N equal to 6, I need to take p to the power 6, that matrix to the power 6. I need to do this. Um, Okay, I have made the job easy for you. Since I had already calculated, I have written the answer. But you know how to do this? Okay, you can do a brute force multiplication. If it's a 2 by 2 matrix, it's probably multiply several times and finally you will get this set of numbers. But other ways you can actually find the eigenvalues. Eigenvalue, diagonalize the matrix. Then taking power 6 is simply directly taking the power 6 of the diagonal entries. Then you need to just multiply with the appropriate eigenvectors to get this. Okay. In the simple case, it doesn't matter. You can multiply 6 times if you have the patience and do it. So now you can ask the question, okay, so I have this p to the power 6. Now the question I have is the following. What's the probability that phone is busy at n equal to 6? Okay. Given that it was free at n equal to 0. So free at n equal to 0 is the initial condition we had already factored in, and all you now need to do is to do this 1 0 and then put in those numbers from that matrix. That's all, and this gives you probability that phone is busy of these two numbers, this one. So that's the required probability. .576 is the answer. So you can see how easily you can compute what you require using this Markov chain approach. And now, not only this, you can actually actually start with any initial condition that you want. The only thing that constrains the initial condition is it should sum to 1. 1 plus 0 is 1, but you can actually put 0.5 and 0.5 and so on. In a phone case, it might not make sense to, because it can't be like half busy and half free, but in a more general setting, all those possibilities are there. Okay, so this is an example of a very, very simple and almost trivial example of what you can do very easily using this approach. But what is of interest is you want to know what happens asymptotically, like what happens as time goes to infinity. Is the phone going to be free most of the time, or phone going to be?
The steady state distribution of the mass of
Yeah, so the question is what is the steady state distribution? So that question is basically about long time behavior. So when I say long time behavior, you are essentially asking the question, what happens to p power n as n tends to infinity? N is much larger. So we can again go back to the first example, the one that we did, and so you have this p which is 3 by 4, 1 by 4, 1 by 6 and 5 by 6. You can ask what is p power n in the limit of n going to infinity. Okay. And here is where it is useful, and in fact you need to do it by finding the eigenvalues, because unlike the case of p power 6, maybe you can multiply the matrix 6 times and still get away with it. There is no real way of multiplying the matrix infinite times. Okay. So in this case, p power n would be so this is as n is much larger than 1. So here is where that approach of trying to find the eigenvalues and doing it is very useful. So for example, if you take this matrix P with elements 3 by 4, 1 by 4, 1 by 6 and 5 by 6, the eigenvalues are, so it will have two eigenvalues, lambda 1 and lambda 2. So one of the eigenvalues is 1, the second eigenvalue is 7 by 12, and the corresponding eigenvector is 1 and 1, and in this case it is minus 3 by 2 and 1. So you can construct a matrix out of these two eigenvectors. So let's call it V, which will be like 1, 1, minus 3 by 2 and 1. So this kind of transformation is called a similarity transformation in general. Okay. So general similarity transformation for any matrix, if I have some matrix A, a general similarity transformation would be something like this. This is the transformation that you are doing on your matrix, and this will give you a diagonal matrix. Provided this is diagonalizable, then you will get this, and this is made up of, this is the matrix that you make by putting together all the eigenvectors of A. So that's what I have exactly done here. You do this, then so with this V, once you have this V, all you need to do is to do this V A or V P V inverse. You will get a diagonal matrix, but you don't need to do that because you already know the diagonal matrix, because the diagonal matrix is simply the eigenvalues along the diagonal. So it will be 1, 0, 0, 7 by 12. Is everyone aware of this way of doing things? All of you know this. Okay. In that case, I would just skip. All of you know this, right? Okay, fine. Okay. So just to complete the story, all you need to do is to calculate Pn, you will simply do this. Okay, so if you do this, of course, you will get exactly the matrix that's given here at the top 0.4, 0.6, 0.4, 0.6. So you can note one thing, you started with the matrix P where the rows sum to 1, and even when you take P raised to the power n, you still see that the rows sum to 1. Okay? So that's a property that it will always retain. So in other words, in the long time limit, to answer the question that we started with, the long time behavior in terms of that phone problem, there are two answers. One is probability that phone is free is 2 by 5, and probability that phone is busy is 3 by 5. Now, the important thing is that it doesn't depend on the initial condition. So, we took 1 0, 5 0 is equal to 1 0 row vector. Actually, it doesn't matter, irrespective of what initial condition you take, you will finally still end up with the same result. Okay. And that's not hard to see because you are actually doing a stochastic process. The system forgets where you started with. So, it doesn't matter where you start with, since you are going through a series of random processes over a long time, it forgets where it started from, and the final answer is independent of the initial condition. So you can go through everything that we did in the last two slides. You can repeat it with some 5 0, which is not 1 0 there. You can even take half half or any other combination. You will exactly get the same answer. So in fact, you can try. I'll leave it as an exercise for you. Try the whole exercise with 5 0, which is a comma b, such that a plus b is 1.
So in the previous problem, could you remind what was the value of P?
Which p?
In the previous problem, what was the corresponding problem?
Okay, so you can try it with this. Choose any value of a and b such that a plus b equal to 1. You will still get the same answer in the long time case. So let's go to example 2 as well, and the example 2 where you had the same phone caller setup, but with the possibility that one caller can wait. In that case, this was our probability transition matrix. Okay, no, actually we wrote the matrix in general. Now I am going to put numbers. I am going to take P equal to 1 by 4 and Q equal to 1 by 6. So if I do that, I get 3 by 4, 1 by 4 and 0. So for these choices P and Q, 1 by 4 and Q equal to 1 by 6, so this is what we have. And in the long time limit, let's say you want to take the limit that n tending to infinity of P power n, okay, and if you do that, the recipe is the same as what we did in the previous problem. Now you can directly identify the limit. So now you can write the when n is equal to infinity. So you are asking what the answer is 2 by 11, 4 by 11 and 5 by 11. So this is what is written here in terms of decimal digits, but in terms of fraction this is the answer. So in the long time limit the probability that phone is free is 2 by 11 for example, or probability that caller is waiting is 5 by 11. So once again remember that this is again independent of the choice of initial state that you did. So now we can generalize some of our observations. So to do that, let me now change the notation just because all the textbooks write it in one way. I am going to write this asymptotic probability distribution denoted by pi bar, okay, which is simply the limit of n tending to infinity of p power n. Okay. So in other words, you have your transition probability matrix P, raise it to the power n, and there is some initial state that is given as part of your problem statement. So you do that P power n left multiplied by phi 0. When you do it infinite times, you settle on to stationary probability distribution. So in other words, the system reaches a steady state. See, the steady state doesn't mean that there are no transitions. It means that you reached a steady state, not necessarily that nothing happens. It's not a state where nothing ever happens. Okay. So just to give you an example of such a thing, suppose let's say I have a ring of n nodes. So let's say I count it like this: 1, 2, 3 up to n. Okay. And I have random walkers here. So this is actually a case where you will actually reach a steady state. You can write a transition probability matrix for this problem, compute what is the stationary probability distribution, that pi bar. So since it is a random walker problem, it doesn't mean that as time goes to infinity, the random walker stops walking. Okay. Stationary doesn't mean that. It just means that the probabilities does not change with time, but the walker would still be walking in such a way that the probability does not change with time. So there is dynamics happening even then. So we can also rewrite it as, for instance, it's also true that if the first statement there is true, it is also true that, see, right now the problem is that you still, given p, you still have to raise it to the power n. You can do a little better because under the same limit that n tending to infinity, this is also true. Okay. So which means that you can write it as and this is simply, so this whole thing is simply equal to pi bar, which means that I can actually simplify it, and so this pi bar, which is the stationary distribution or vector representing the stationary probability distribution, is simply the eigenvector of p corresponding to eigenvalue 1. Okay, because this is exactly an eigenvalue equation with eigenvalue 1. So I could have written it as, it's the same thing. So this quantity pi bar is called the stationary distribution or steady state distribution. Or an invariant probability distribution. Obviously invariant because it doesn't change with time anymore. Okay. And the important thing to notice is the way it is written. You are probably more used to eigenvalue equations written like this. Okay, there is a matrix and there is a column vector, but it's identical to that, but just that this pi bar is the left eigenvector of P. That's because of the peculiar structure of P that it turns out that it's left eigenvector. But if you go to, I don't know how many, I don't know in MATLAB at least, if you have used Mathematica, there is no way to directly calculate the left eigenvector of a matrix. There is only one eigenvector, calculate eigenvector, but it's not hard to find a workaround because left eigenvector is simply eigenvector of the transpose of the matrix. So if I have to find pi bar given P, all I need to do is to take transpose of P and find its eigenvector. That is just the left eigenvector of P itself. Okay. So that's how you need to do. So you will find this one, this V will be identical to that pi bar there. Okay, so we'll take a break after just 2-3 minutes. So let's go back to, let's just consider some general lessons from here. We'll go back to the two-state chain, which we wrote it as 1 minus P, P, Q and 1 minus Q, where P and Q are between 0 and 1. And in this case, the eigenvalues are uh, 1 and 1 minus P minus Q. And you can diagonalize this matrix. Okay, so let me directly write the result. So I did the diagonalization, finding the eigenvector and all that, but I leave it to you as an exercise to try out yourself. But if you do all that, you can finally ask what happens as n tending to infinity of P power n. You will get it as P by P plus Q, P by this one, and this is simply equal to pi bar and pi bar, where pi bar is the first row and second pi bar is the second row, obviously. So typically the dominant in all these cases, there is a structure to it in the sense that as you see, P of course sums to 1 along the row, and the largest eigenvalue is always 1. And the fact that largest eigenvalue is 1 and all other eigenvalues are less than 1 basically is the reason why a matrix like this converges. No, you can always ask the question, why is that limit even existing? Some arbitrary matrix you constructed out of some transition probabilities. Should the limit n tending to infinity of such a matrix ever exist at all? So it's because of a structure which is inherent in this, that the first eigenvalue is always 1, second, third and every other eigenvalue is less than 1 in modulus, that in fact this converges. Now from this point we can generalize this and do somewhat more complicated problems. Okay. So I'll stop here. We'll take maybe 10 minutes break or so, 10-15 minute break, and then reassemble.